Hi, it's time for another math easy solution to discuss further into applications of integrals and now look at this concept, the concept of the area of a surface of revolution. And it's similar to my earlier videos, which I went over arc length or length of a curve, as well as the area of an integral or area under a curve or the volumes, etc. But now we're going to develop one for the surface area, and I'll get to that in a bit. Basically, a surface of revolution is formed when a curve is rotated about a line. And such a surface is a lateral or side to side or whatnot boundary of a solid of revolution of the type discussed in my earlier videos on integrals and volumes. So if you recall before, you could form a shape just by rotating around the x-y axis or any line, etc. This time, instead of dealing with the volume, we deal with the surface area. So now we want to define the area of a surface of revolution in such a way that it corresponds to our intuition, and I'll get to all this in a bit. Basically, if the surface area is A, we can imagine that painting the surface would require the same amount of paint as does a flat region with, and this is an area. With area A. Basically this is saying if you were to flatten out a shape, and then that would be that surface here, and I'll get to it in a bit. Basically, let's start with some simple surfaces. The lateral surface area of a circular, circular is a typo there, circular cylinder with radius r and height h is taken to be A equals 2 pi rh, because we can imagine cutting the cylinder and unrolling it to obtain a rectangle with dimensions 2 pi r and h. So basically, if we were to draw this out, if we have a cylinder like this, where in this case we have, so it's like this, the radius is, this is radius r, and the height is h, and basically if we were to cut this across like this, let's just make a cut here and say cut. So if we cut it and then we unravel it, I'm just going to draw this. So it's a cylinder like that, and then let's say we cut it across here, and then when we cut it and unravel it, we get something like this, and we just get a rectangle. I'll just draw this better. So we get a rectangle where this was the height, and now this length across, remember this whole circumference around here, so the circumference, if you saw my earlier videos on proof for the circumference of a circle, this just equals 2, and you can see that in the video link below, this just equals to 2 pi r. So this circumference, when we unroll it, it would look something like this, where this length would be just 2 pi r, which is the circumference. And now what we have is basically this area, again, area is defined as multiplication between height and width here. So the area is equal to 2 pi r times h. And that's the area, and that's considered this surface area if we were to highlight this across. So this is that surface area that we are trying to derive. And likewise, we can take a circular cone with base radius r and slant height l and cut it along the dashed height, as I'll show in a bit, and flatten it to form a sector of a circle with radius l and central angle 2 pi r divided by l. So if we took a cone, so like this is a cone right here, and let's just draw a dashed line for behind it just to show it's 3D. So basically, if this is the radius r right here, so that's radius r, and now if we were to cut across here and cut across like that, where this length is l, so that's the length across, put it like that, and that's this length, and that's a slant height or slant length across like that. So we make a cut here, and then if we unravel it, we get a sector of a circle. So if we just picture the cone like this, roll it around, you can try it with paper, etc., you will get basically a cone. Yeah, so when we unravel it, it would look something like this. Yeah, so I'll just draw this across like this. So we have a sector of a circle, and where the central angle is here, this is our theta. And again, the slant length is this. And this arc right here, that is just the circumference. That's just this whole round part here. So the circumference here, same with the circle, is equal to 2 pi r. So that this length across, this arc length, is going to be 2 pi r as well. So 2 pi r like that. And now if we recall the definition of radiance in my earlier video and the angle right there, so recall that by definition we have, and you can see that in my earlier video on radiance and angles in my video link below. So we have like this angle is theta, this is arc, this is the radius, and this is just as a part of a circle. Then what we have is theta is equal to arc divided by radius. So this is by definition of a radiant. So applying it up to here, we get this central angle right here. Theta is equal to arc divided by radius, which equals to 2 pi r divided by L. So that is the angle right here, the central angle of this sector of a circle. And now the surface area of this cone, that one is just basically the area of this this flattened sector right here, sector of a circle. And if you recall from my earlier video that I proved that in general, or pretty much for any angle, the area of a sector of a circle is basically, if we have like this is theta, if that's theta, this is the length like that, L, then the area is simply 1/2 L squared theta. Yeah, L or R, this is just the radius, so we have that. So in our case, we have theta is equal to 2 pi r divided by L. So the area of the surface area, or the surface of the cone, is simply 1/2, and then L is the same thing, L squared, and then we have the central angle 2 pi r over L. And this equals 2, the 2's cancel, the L and this cancels, and this just equals to pi r L. And I'll just circle that. So now that we've covered these basic simple shapes, a cone and just a cylinder, now the question is, what about more complicated or just in general surfaces of revolution? So if we follow the strategy that I covered for defining arc length in my earlier video, we could approximate the original curve by a polygon. So that's the strategy we use. We would approximate the curve and then again sum up to infinity. In this case, we're going to approximate the curve similar to the arc length method, and then this time we rotate it across and sum up to infinity, etc. We'll get to that in a bit. So when this polygon that we approximate the curve or the arc with a polygon or just straight line segments is rotated about an axis, it creates a simpler surface whose surface approximates the actual surface area. By taking a limit, we can determine the exact surface area. This is similar to all the integration, integrals, volumes, areas, arc length that we've done in my earlier videos. Thus, the approximating surface would consist of a number of bands, each formed by rotating a line segment about an axis. So again, we look at small parts and then sum it up. To find the surface area, each of these bands can be considered a portion of a circular cone as shown in the figure below. So basically, we'll get to this, or we'll put all this together and then we'll start making more and more sense. So we would approximate it, but when we rotate, let's say a line, let's say something like this, if this is part of a curve and we rotate it, it becomes something like that, and then it goes something like this, and then draw it in 3D. Actually, it's going to be exactly like this. So consider this the line segment, and then when we rotate it about about a line or an axis, etc. So we get something like that. So we get a cone like this, or part of a cone. And I'll just draw it like this. I'll call this R2. I'm going to draw this and make it look 3D. So when we have something like this, where if this goes all the way to the top of the apex, and if we draw a line like this, you could approximate it by a polygon, by a cone. Yeah, here I quickly just made the drawing a bit better. So what we have here, and again, this is our length L. I'll just draw it like this actually. So that's the length L of the curve of the line that we're rotating about this line, and then here we'll call this R1 because it's smaller than this. This is our R2, and then we'll call this length L1. And I'll show you why we're doing this way. Yeah, we're basically doing this so that we can use this full cone to approximate this surface area that we are rotating it about. This that we formed from rotating it about this line right there. So the area of a band, in this case the band is going to be from this L distance here, or frustum of a cone. The frustum is basically the bottom part of a cone left over when you cut the top part off. So with slant height L, so that's the L, and upper and lower radii R1 and R2 is found by subtracting the area of two cones. And that is why we're doing it actually. So we can solve this surface area by subtracting the overall from this part right here, from the L1 slant height. So the area, or the surface area, is equal to pi R2, so that's the full one. Yeah, times it by, this is L1 plus L. And again, this is the area of a cone that we just derived above. So we're going to use the same area right here. That's of the cone, so pi RL. So that's surface area. Now we subtract from the smaller one. So we subtract from this small one like this, etc., versus the big one like that overall. And then we just get the in between. So when you subtract the top from the bottom, you get that. So now we get pi r, this is 1, the small one, and this is L1. And now when we simplify further, take the pi out, and then multiply this inside, we get something like this, R2 L1 plus R2 L1, then the pi's out, R1 L1. So this all together equals to pi, and then this is in brackets. We're going to simplify by removing this L1 out of there, so we get this R2 minus R1, so we just factored the L1 out. Actually, this one is L, yeah, my bad, the fret that one, when you multiply that's just by itself. And now we have, this is L1, and then plus just this R2L. And now we can further simplify this by trying to get rid of this this L1 right here. And to do that, we can just basically recall similar triangles. Again, you can see more about this in my earlier videos. So recall similar triangles. So what we have here is, in this case, if we were to take the cross section of the cone, this basically looks something like this, where this was R1, this is R2, this is L1, this is L. So the similar triangles is the ratio is the same, so L1 over R1 is the same as the ratio of this full length over this R2, L1 plus L over R2. So if we simplify this, multiply this out on the left and right side, so put this on there, put this across, we get basically, so we get L1, this is R2, equals to R1 times L1 plus R1 times L. And now what we're going to do is move this over here and then factor out the L1. So we get across here R2 minus R1, because we're subtracting, taking it out, L1 like that, equals to R1 and then L. So there is this part here. Now we can just plug this part which is this right here back inside. So all we're dealing with is R1 and L. So we got rid of this one here. So we don't need to deal with that variable. So thus we have the surface area equals 2 pi. So again, R2 minus R1 L1 plus R2L. Plug this inside. This equals 2. Let's put that like that. This equals 2 pi. And then this is R1L. And then R2L. I'll put this in regular parentheses. And just here we could factor out the L out of there, so we get basically the surface area of that band is equal to pi, and then this is R1 plus R2 times L, like that. So there it is. Or what we could also do, or if we consider the average radius. So if we consider the average radius instead of this R1 and R2, so we consider the average radius R just by itself, R equals 2, the average of these two radiuses, radii, R1 plus R2 divided by 2, then basically we have, then if we just multiply this out, we get R1 plus R2 equals to, move this over, equals to 2R. So now we could plug this back into there. So we could plug that back in. So what we have is thus A equals 2 pi, and then R1 plus R2 is just 2R. Or I'll write this out, 2 pi R, which is the average, times it by L. And there is our, and there is our formula, our simplified formula of the surface area of a part of a band of revolution that we used to, it's a straight line curve and rotated like a cone, or the bottom of a cone. And now we're going to put all this together and apply this formula to our strategy of defining it for just a general function. So consider the surface shown in the figure below, I'll draw it soon, which is obtained by rotating the curve y equals f of x from x is greater than or equal to a, less than or equal to b, about the x axis right here, where f is a positive and has a continuous derivative. So f is positive, it's a typo. So if we were to draw this out, we have, let's draw this out. This is the xy axis like that. Actually, it's too high up. I'll draw it like this. This is the x, this is the y. And now if we were to draw just a random function like that, this is our y equals to f of x. And now so let's draw our parts here. So this is the y equals f of x, and then this is from x is less than or equal to b. That's this point right here, and this is up to here where it's greater than or equal to a. So this is the interval that we're defining it, and it's positive and it's continuous derivative, so it's just continuous everywhere. Derivative is continuous too. And now what we'll do, I'm just going to move this away actually, just to get it out of there. So we're going to rotate it about the x-axis right here. So when we rotate it, we'll get a curve that looks like this. And then this is just, I'll draw just identical formula like that. And then this is rotating it. So we get something that looks kind of like this. Pretend it's exactly identical. And now I'll just draw this, just the 3D part of it, so it's rotated across. So we have a surface that we are trying to get the surface area of all the way around it. And it's the full surface area, so imagine it in 3D. And now likewise with the arc length formula, the area of integrals pretty much, and the volumes, we're all going to look at small subintervals and sum it up. So basically in order to define its surface area, we divide this interval from A to B into n subintervals with endpoints x0. So basically if we were to draw it all across like this, we'll have the x0 is equal to a, then x1, etc., x1, x2, x3, all the way to xn. where this is our x and equals b right there. So we have it equal widths of delta x, and these are all delta x. I'm not going to draw too much into that. This is all similar to what we've done before as we did in determining arc length, so make sure to watch that video. And basically when we take these parts right here and we're just going to rotate these all around it. So at this point here, this is going to be a rotation like that, etc. across, etc. So I'm just going to ignore that. So what the idea is, just break it up into a bunch of bands. So now if yi subscript I is equal to f of xi, then the point pi of where xi and yi are inside lies on the curve. So if we pick this point, let's say here, let's just pick a random one inside, we'll call this xi, then basically this point right here would be this distance across. I'll draw this. I'll draw it like this. So this distance would be yi, then this point, we'll call it pi. This is going to be our just xi, yi. So that's contained in those 2 points. Or I'll just remove this here. So that's our pi, where pi contains xi and yi. So that's at that point, lies on the curve, in the part of the surface between xi minus 1 and xi. This is the, let's just move back one subinterval, so we move over to here. This is xi minus 1. Is approximated by taking the line segment pi minus 1 to pi. So this is the line segment, that's how you would write it, point 1, point 2, and basically rotating it about the x-axis right here. So if this is xi minus 1, then likewise, if we draw it across, we would get to here. This is our pi minus 1. And now this, and then if we were to draw a line segment, I'll draw this in red. So if we were to draw one like this line segment right here, this distance across is going to be our pi minus 1 pi. So this is just saying a line segment from point A, from this point to this point. That's all it is. And it's a straight line like that. And then we're going to approximate, this is part of the surface between here is approximated by taking this line segment and rotating about the x-axis. So this is the curve. This is exactly going to be like our bottom of the cone. So if we recall here, this is looking at a vertical, but if you turn it around, it's the same idea. So we take this straight line. This could be this could be like our point from point I minus 1 to point pi. So we have this, and we rotate it across to here. Or actually, let's just draw it a bit better. Yeah, I'll just draw this a bit better. Let me just zoom in. So let's just draw this exactly down here. Pretend it's perfectly symmetric. So we draw this line from there to there. And then we just pretend it's a straight line. It's just a bit hard to draw it. And then we rotate it across up to this point, and then this rotates across like that up to here, and then obviously behind it you're gonna get the 3D like image. Yeah, it's gonna go something like this, and then this side here is also gonna be our 3D image, etc. And so this is what we are approximating, this band across here that goes all the way across, and then on the back side as well. Yeah, so the result is a band with slant height. This is L is going to be equal to the absolute value of these points, because we're not dealing with any negative numbers. So pi to pi1, this is just the same thing as saying the distance across, because distance is not negative. Distance is always the positive. Yeah, so this is the new slant height. So remember, this is the exact same thing as I was showing here. So the slant height, if you go all the way to this frustum, I think that's what it's called. So that's the slant height. If you rotate it, the same thing. From it's the same idea from the point this one to this one. So yeah, so its surface area is going to be, well, that same formula right here, 2 pi r and then L. So area is equal to or I'll just because we're gonna use A for something else. So the area, the surface area, I'll just write as A of the band I is equal to 2 pi, and then the radius is y yi, and not yi, it's the average radius. So the average radius changes. So this is yi, but then from here to here, this one is yi minus 1. So the average radius is gonna be, scroll back here, average radius r1 plus r2 divided by 2, that's just common here. So this average radius is gonna be yi minus 1 plus yi divided by 2, and then L. And then the slant length L, again this formula L is just that length we were talking about, that's just distance across. So that's just distance, or absolute value, 0.1 to pi minus 1 to point pi. So that's just a random band we're gonna pick. Yeah, where again we have this is where average radius, or actually the other way around, I'll just write yi minus 1 plus yi divided by 2 is equal to the average radius. And now if we recall from the proof of the arc length formula that I went over in my earlier video, I showed that, well, basically this length right here, or this distance across, is simply, or not simply, but it is this distance right across. You can see that in my earlier video, you can see that video link below, is just going to be equal to the square root of 1 plus, and then this is the derivative of that curve function up to xi star, and I'll get to that in a bit, times it by the width of that band. And where this xi star, like I went over it, is just is some number, it's just any number, or not any number, it's just some number in xi like this. Yeah, some number inside between the interval xi minus 1 to xi, and it's basically some number in here where you're found by using the mean value theorem, where, like I showed in my earlier video, this is basically the derivative, or the slope is the same as this right here. So you can see in my earlier video, this is by mean value theorem. Value theorem right here. Basically, just for completeness sake, just the derivative at this random point is equal to basically this average slope, or the slope of that line. So run or rise over run, so f of xi minus 1 divided by delta x. Anyways, you can see more about that in my earlier videos on mean value theorem and the proof for the arc length formula. So now that we have this, we could plug this back in. But before we get that, basically recall that, well, when delta x is very small, what we have, so if it's very small, it's going to be roughly equal to xi, or xi minus 1. Very small, we have, so if you're taking an infinitely small delta x, or the width of the band, then basically yi, which equals to f of xi, is approximately equal to, well, f of xi star. So that's the point inside. And also, same thing on the left side. So basically when you get it really, really small, f of xi and f of x minus I are roughly the same. Equals to f of xi minus 1, which also equals to the f of xi star. Yeah, and since the function is continuous, it's not an issue, there's no giant spike or anything like that. So this is basically saying the limit from either side is going to be approaching the same number. So now when we plug all this in, so thus when we have small delta x, thus the area, surface area of the band, SAI equals 2, it's going to be equal to 2 pi, and then we have our yi minus 1 plus yi divided by 2, that's the average radius, and then this is our pi minus 1. This, I'm just writing it like this, and then we're going to write it all down. So that's just this part right here. And now when we plug in everything we just found, this equals 2. Yeah, this equals 2. Well, let's look at it. This yi plus yi. Well, first these 2's just cancel. This part right here, that's just going to be, well, they're both f of xi star, so this is going to be f of xi star. And now this pi minus the pi, this equals 2. Yeah, this equals to just that square root formula I just showed above here. So this all together equals 2. Now we have just 1, 2. So 2 pi f of x I star. And then we have square root 1 plus, and this is the derivative xi star. Try a better star. Squared, and then delta x. And thus, like always, basically an approximation to the area of a complete surface of revolution is when we just sum this up to the n subintervals. So what we have now is approximation of the total surface area, SA, is going to be, well, roughly equal to the summation. Yeah, the summation like this of from I equals to 1 up to n. I'll draw this a better summation like that. And we just plug that in. So 2 pi f of xi star delta 1, square root 1 plus f of derivative xi star squared, and then delta x. And now basically this approximation appears to become better as, well, n goes to infinity, and then again recognizing the above function as a Riemann sum, and this is just a Riemann sum of just anything I have, like from this summation from I to n, I equals 1 to n, and then you have this delta x, and you have this function here. And you can also learn more about that in my earlier video on area of a function and Riemann sums. So basically the idea is just to sum this up to as it approaches to infinity right there. So this what we have is basically the area is going to be equal to it. I'll just write this out. When we sum this up, limit as n approaches to infinity. So we're going to have n infinite and infinitely small subintervals. So the limit of as I approaches of I equals 1 up to n, we have of this function 2 pi x I star, and then delta, square root 1 plus f, the derivative xi star squared, and then delta x. This equals 2. Yeah, this equals 2 by definition, and like, well, not definition, like I proved in my earlier videos. This is, and also, yeah, by definition. So integral from a to b of 2 pi, and then this is just going to be f of x, and then this is going to be 1 plus, this is f of, I'll write this with a bracket like that, the derivative f of x, and then instead of delta x we have our d of x, or infinitely small, infinitely small width or subinterval. Yeah, and so now that we've basically derived the surface area of the entire approximation, or just of the entire shape formed when you rotate that curve around the function as an integral, thus we could just sum it up. Thus, in the case where f is positive and as a continuous derivative, we define the surface area of surface area obtained by rotating the curve y equals f of x from x is greater than or equal to a, less than or equal to b, about the x-axis as, when we finally sum it up and write s for surface area, and that just equals to the integral from a to b, and that's just this top function right there, 2 pi f of x, and then this is 1 plus square root 1 plus is the derivative squared, and then dx like that. And let's just circle this up. And with Leibniz notation, because we have this derivative inside for derivatives, and like just similar to the arc length formula that we wrote in Lebanese notation. Again, you can learn more about this in my earlier video. Basically, what we'll have is the surface area. Let's write S is equal to the integral from a to b of 2 pi f of x. And then we have this 1 plus, and now we have dy over dx. And that is how you write the derivative in Leibniz notation. And then we have this dx that's squared, and we have dx over there. And similarly, if instead of we're dealing with y equals x, let's say we were dealing with with x equals g of y. So instead of that, we were for the interval from y is greater than c and less than d. And this time we're dealing with rotating about the y-axis. And the formula is simply just the same, but just flip over the dy dx. So we have the surface area would be then from integral from c to d of 2 pi, and then this is going to be 2 pi actually at g of y. Actually, I've made a mistake here. This would just be y. Well, not a mistake. This is the same thing. But the notation is 2 pi y. And now here would be 2 pi x, and that's because that's our new function that we're dealing with. So x is the function, or the dependent variable on the independent y. Now we have this is going to be dx over dy, so derivative in terms of y right there. It's squared, and then we have this dy as a subinterval, or infinitely small subinterval, because we're dealing it vertically, and I'll graph that out soon. And now we can even simplify this further. Basically, both formulas can be summarized symbolically using notation for arc length, of which I covered again in the arc length proof video, and the arc length as a function video. So basically, for rotation about the x-axis, surface area becomes, this is the one about the x-axis here, that's just 2 pi y, and then basically s is equal to integral. And so it's symbolically 2 pi y and then ds. Or this is going to be considered the the circumference times this is the length of the curve of the this interval of the curve. Then you sum it up to infinity. Let's write this like that, where the ds is equal to, so we're just writing that as it. So 1 plus dy over dx. Squared delta x, dx. And similarly for rotation about the y-axis, surface area formula becomes symbolically s equals 2 integral from 2 pi x ds, and in this case where ds is equal to the square root 1 plus dx over dy. So this is the x instead of y, and then this is going to be squared dy. Yeah, and now these formulas can be remembered by thinking of 2 pi y and 2 pi x as the circumference of a circle traced out by the point x and y. On the curve as is rotated about the x-axis or the y-axis respectively. As shown in the figures below, which I will draw it out. So the first one, rotation about the x-axis, or the curve is integral from, so the s is the integral of 2 pi y ds. So what I mean by the tracing it out in the circumference, so if this is the y, that's the x-axis. So let's say we have a curve like this. So we have this curve like that, and this is the point x and y, and then so the circumference of a circle traced out by the point x and y. So this is the point, and then if we trace this out, it looks something like I'll first rotate it across. So if we rotate it, looks something like this, all the way like that, and then this goes like that. Put this together. I'll just draw a perfect shape like that. So you can just don't mind my drawing, it's not too good. So it looks something like this, and then this point right here, you could look at it as a circle, so it's going to be a perfect circle. Where the radius here is just y, that's the radius, and then when we rotate it across like that, yeah, this point right there, this circumference of this circle, circumference, is just going to be 2 pi radius or 2 pi y. And again, the area that we're covering is this all put in red, so that we're just shading it and everything. So it's the surface area across it and on the backside. Yeah, and this ds, that's just an incremental distance like this, ds across from this point to that point, here ds, etc. And now for the rotation about the y-axis is the same idea. So if we had, let's say we had a curve like this, so this curve, this point here is x, y, and then when we rotate this about, we get something like this. Draw it like that. Just rotate it again. I'll just draw a perfect, trace it across, circle it, and then so we have something like that. And then when we rotate it across here, like that, and then this radius across, this is a radius going to be x now. So the circumference here would be, let's write circumference equals to 2 pi, and then radius, which is x. And then the ds, or the incrementally small curved length, it's going to be something like this. That's our ds. So it's from this point to that point across. So anyways, and then yeah, basically that's the idea. And then this time the area or surface area generated by the rotation is just crossed like this, and on the back side as well. Yeah, so anyways, basically that's all for today. Hopefully you learned from this pretty extensive proof video or derivation video of surface area for a general function, and then later videos will go over some examples just to illustrate how to solve this. And it's again, it's a bit tedious and extensive here, but the idea is same as what we've been doing before. Use simple shapes to approximate a small section, and then basically make that section infinitely small, and then sum to infinity, and then use the idea of summation, Riemann sums, to write it as an integral. And yeah, so that's pretty much it. So anyway, that's all for today. Hopefully you learned from this pretty extensive video, and like always, you can download these exact notes in the link below. And thanks for watching.